Right, so we're going to do this part of the video. We're going to do 1.3.3 networks. I'm going to cover this and mostly this. A lot of this was covered in the GCSE anyway, so hopefully it won't be too many videos. But there we go, so let's get on. So, okay, so we've got topologies. You've got two types of topology, and a topology is a layout of a network. I'm not going to go through, by the way, the beginnings of a network. So I'm assuming you're at GCSE level. If you've not, then watch those videos first of all. All the networking videos are for GCSE because all of it is covered in the A level, and then come back to here. So you've got a physical topology. So in the last course we just looked at topology, which was just the layout of the network. But now you've got the physical layout, which is literally the position of the computers. How are they placed in the buildings? How's this going to affect building work? And then you've got the logical topology, which is where is the data going to flow? How are they connected together? These are completely independent, but obviously you would think about them logically. You'd position things correctly to make it easier and cheaper to design and place things. You're not going to connect computer A, computer B logically and then stick them 7 miles away physically. This would seem unwise. So anyway, so that's what topology is, right? Physical is the physical location. Logical is how the data flows, like how are they connected. So let's have a look at one of them. Let's look at a physical bus topology. So basically, there's a big cable that goes. Now, if you most classrooms would be like this. There's a cable going round in a box around the edge of the room, and all computers will pipe into that cable. It's only used in LANs, obviously, because kind of a cable go around a massive area. It's cheap to install as you need less cable, and you don't need any specific hardware or anything. But of course, if we cut the cable here, then all of them are going to get lost. We can easily add a sniffing packet to it for security. So if we can access this one wire, all data is going down this wire, so that's not good for the network. Quite insecure, and not very secure. And if there's heavy traffic, you can get a lot of collisions, and it can be slow as all the data's got to go down the same cable. So easy to set up, but has its weaknesses. Okay, but quite good for like a classroom layout and things like that. So let's go on. Physical star topology is what you've probably got in your house. So basically, computers connect to a middle node. So by the way, sometimes these things are called nodes. Okay, so this is a central node here. Probably should have coloured that differently to make it look more important. Let's colour it to yellow. So that could be a server or a router or switch, which are covered in the GCSE, obviously. Yeah, and that's what a star network is like. So it's easy to add new devices because Bob comes along and you put a new computer there and you attach it. This could be done wirelessly, of course, which we'll talk about later. And a single cable being cut will only normally affect that computer that's using it. It's more secure because this computer never gets to see the data from this computer here. If I get access to that route, then it's not any others. And obviously there's less collisions, so there's more likely to be faster. There's different cables, faster than a bus, really. Obviously the weak point here is the central node or router extension. If that goes down, then everything's gone. And obviously it can be more expensive than a bus, as you know, there's obviously more cables. Okay, so then we've got a mesh topology, which is what the internet uses, or at least uses a partial mesh. So a full mesh is where every computer or node is connected, to each other. And as you can see, this gets quite costly with cable and connection, or that could be done wirelessly. But the reason it exists is, let's say this cable gets cut, we can still talk. So I can go down this cable and then this cable. So it's quite good for something like the internet, where you want to ensure that there's connections around. There's a lot of rumours that the internet was originally developed for that. America sort of pushed the internet quite a lot. So they were worried that sort of Russia would nuke some of them and take out a whole area. And they wanted a way of having data to still get round. And they thought the internet would be a great communication thing during the war. It's been a bit sort of is this true or not? Who knows? I mean, Al Gore's involved in this. There's a lot of talk about this. So who knows? It's a sort of myth. Is it true? Is it not? But anyway, so what are the advantages of mesh? Well, obviously it's really fast because data can take many routes to its destination. Obviously, if this is going slow, it can go round. Failures of many cables and nodes don't actually take down the network. But of course, lots of cabling costs, and it can be expensive to add a new device because you put one more device in now, and I've got to do loads of cabling. I've got a cable from there to there, and then there to there. And if you're asking what's a partial mesh, well, a partial mesh is like that, where they're not. There's quite a few connected together, but they're not all connected to each other. Whereas a full mesh, every device is connected to every other device. I don't know if I've done it there. I've lost interest in drawing cables, if I'm being honest. I think that's it. Actually, no, because this one should connect to this one over here as well. So you can see it's getting quite silly now. But yeah, so that's obviously lots of cabling and annoying to upkeep. So wireless, how will that affect the topology? Well, the thing is, wireless can make a lot of things that were more difficult a bit easier. So Star, for example, is super easy with wireless. You don't need any cabling at all. And generally, the benefits of wireless is that there's no cables to trip over and that no building work, really, because you don't have to put cables around. But there you go. So let's move on. Protocols, right? I'm not going to go through protocols because it's all in the GCSE and it's no different. A protocol is simply a predefined set of rules on how to communicate over a network. So it's like how we're going to send data, how we're going to chat. There are various different protocols you need to learn. They're in the GCSE. A standard, which is in the GCSE, but I don't know if I mentioned it enough, so I'm going to say, is an agreement where basically sometimes they're official, like Bluetooth's a standard, Wi-Fi is a standard, Ethernet cables are standard, or Ethernet protocols are standard. So basically, it's where companies use the same technology, even if it's not made by them, and this allows compatibility. It's better for the user, and it allows software and hardware to talk to each other, work together, even from different countries. Another example is like phone charger cables. I don't know what time you're watching this, but Apple have been forced in Europe to use USB-C to unify the standard of phone charger cables because they felt that wasn't good that they use different cables. So things like that. USB is a standard. You know, if you buy a new device, it's probably going to have USB on it. You buy a TV, it's got USB on it. It's got Ethernet. It's got Wi-Fi. It's got Bluetooth. You know, things like that. And that's what a standard is. Yeah. So, right, this is get to the more interesting stuff or the more tricky stuff. So how is the internet structured? Okay, well, it's a massive WAN, obviously, and each continents have this backbone cable which connects across the globe, usually underwater. They're absolutely huge. They use these big ships to drop them in. They sink to the bottom of the ocean. And your national ISP, although obviously in America and countries like that, there'd be loads of them, will connect to these backbones and then they'll sort of feed out to the smaller internet service providers to allow you to connect to them yourself. So what's a fully qualified domain name? Well, you've probably heard of URL, Uniform Resource Locator, or web address, but a fully qualified domain name is just the domain part, okay, which is this bit. Now you might think that is a URL, but technically it's not, and I'll explain in a minute the difference. So you've got the subdomain, which is www. It doesn't have to be that. It can be mail. It could be other www2. All right. Then you've got this part. So this is the full domain. Okay, and we'll go through what these things mean in a bit more details. This is the root domain. The whole thing is the root domain. And this is important to know. TLD and this is your top level domain. So you're in UK, and your second level domain is .co. And we'll go through what those mean in a minute, but you just need to understand which bits. You might need to be asked what's the difference between that and that, or what's the routing or something. But there you go. So what's the URL then if this is a domain name? You know, the subdomain, the domain name, the fully qualified domain name, sorry. Right, well, a URL also includes the resource. That's why it's called Uniform Resource Locator. And the protocol is normally in there as well. But the important thing to remember is that, in fact, because it's called Uniform Resource Locator, it also includes, like, if there's no, by the way, second level, then it's just this is top level domain, just the whole thing. It includes the resource. Now you might say, but I don't type that. But actually, what's happening is the browser is typing that or something similar, even if you don't say it. Oh, just one last thing to mention with this, which I've forgotten here, so that's naughty. Technically, fully qualified domain names end in a dot. I don't think it's going to be important to the exam, but the web browsers should delete that. But technically, they do end in a dot, but I don't think it's going to be important for you to know that. But no, so here, for example, yeah, there's normally, there even could be like title or something, like, and that would be the element that you're after. But yeah, so the resource is the extra bit, okay? That's why it's uniform. So it includes a fully qualified domain name and more, right? So where are we? So you make sure you've watched the GCSE videos on what's an IP address, a MAC address, DNS, and URL. Obviously, we just covered there anyway, because otherwise the next bit's going to make no sense. So DNS server structure. So on IP4, now currently we're using IP4, which means that it's a way of naming the IP addresses. So at the moment, IP addresses are 4 digits, and we're running out of unique numbers with those 4 digits. So they're bringing out IP6, which is out now, and there'll be more. But right now, we're using IP4, so 4 8-bit digits for each computer. Okay, and then there are 13 root servers labeled A to M, and certain countries might come under a server. For example, let's go here. So this one means A server. This is theoretical. I don't know if this is what it comes under. All right, it's just theoretical. Okay, so A, which server A? Root DNS root server A could have .uk, and it could also have .com. So all of .com could be under here. So all of the DNS for .com. Every website that's got .com in it, it's got the IP address and the domain name here. And then this one would be broken down into subparts because it's that's the top level one. This is the second level one. And then all the .co.uk's would be under here. All the .all.uk's would be under here. And that could be under DNS server A or whatever. And they all have, they work together to have all of the, where are they? I've lost the form. Yeah, so to have all of them under their thing, right? So, how would you resolve an IP? So let's say we're going to www.test.org.uk. Well, they go from right to left. Okay, so and just to be clear, this is only just to go back. This is only theoretical. It doesn't mean that .com or .co.uk are under A in any way. Just to be clear, that's just a theoretical structure. .co.uk could be under all of them. You know, various things. Anyway, it goes from right to left. So basically, it will look for that. And then it will check your local DNS, and then if it doesn't find it, it will go for the root DNS, and then the root DNS will say, well, I don't know what that is, I'll ask this one, and then it will say, yeah, I'm UK, it's me. Oh, brilliant. Okay, well, now I need org. So now we go, right, have you got org? We go, yeah, I know org, it's here. And then it will go test, and it will go, yeah, I've got test done it, and it will go right to left, and it will find the DNS in like a binary search tree, basically, sort of. Down until it gets the DNS of the website, and then it will return the IP back to the person as described in the GCSE. So you need to add this level to that kind of steps of checking the DNS. So you're going to put it in the browser is going to check the local DNS, then it's going to check the root DNS, and so on and so forth that way, and then it will get back the IP and the web browser will show it. So make sure you have that in your answer. So last but not least, how do you get registered? Well, there are currently five global internet registries that work together to keep a copy of every domain name. Okay, they have to be unique, and you have to purchase it, and then you register the IP that's associated with the domain name. So you buy www.happypeople.com, and that gets registered with these five global internet registries. And then you would therefore tell them where your server IP is. I think it's a pay now. It used to be free, but I think that's a pay to change now. But yeah, so you then say that www.happy, whatever the thing was I just said, would be at 42.84.91.281, and that would be its IP address. If your IP address your website changes, you'd have to let them know. I think they charge you a small fee, and then they change it on their registry from then on. Okay, so that's this part of it. So we'll go on to the next bit.